Hi, and welcome back. Brian at AutoShopTeacher.com, and in this lesson I'm going to review the ASE A1 practice questions and kind of do an introduction about this test. So let's look into this here a little bit. What do we have? Let me make that a little larger on your screen. So in the A1 test, you can see that about 30% of the questions are going to be general engine diagnosis, around 20% based on cylinder head and valve train, another 20% on engine block diagnosis and repair, a few less on lubrication and cooling systems, even less, about 7 with fuel, electrical, ignition, and exhaust systems, for a total of 50 scored questions. And I want to emphasize that's 50 scored questions. You're actually going to have 60 questions when you take this test if it's the first time. You're going to have about 75 minutes to complete the test. So dividing and doing the math there, you're going to have about 75 seconds or 1 minute, 15 seconds per question. If we were to sit here right now and run off a minute and 15 seconds of dead air time, it would seem like an eternity. And I just want to remind you that don't get freaked out if a question you're having to give it an extra few moments of thought, okay? And as we go through these practice questions that come straight out of the 2023-24 ASE Study Guide, look them over. And I'm going to be talking about these. I believe we have 9 or 10 questions in this series for practice. We'll go over ways where you can maybe eliminate 2 or 3 of the possible answers, and in doing so, come up with the answer that you want to select for your answer. So continuing on here, expect 10 additional questions. Those 10 additional questions are basically questions that ASE is testing their validity. If a bunch of people get them wrong that have scored well on the rest of the questions that were actually scored, then those questions never actually make it onto a test as a scored question. It's the way ASE tests questions before they're actually scored. Keep in mind that if Espanol is your primary language, that on the A1 through A9 test, it does have an option button where you can select to take your test in Espanol. So let's get into these questions here. Question number 1, an engine makes a knocking noise when the transmission in drive. The knocking noise is not heard in park or neutral. Which of these could be the cause? So as I'm going to go through each of these practice questions, I'm going to read the answers, and then I'm going to, on some of them, go through kind of a process of explaining how we can arrive at our answer. Also, while I'm talking, if you're feeling that you're already pretty competent in the A1 subject matter, just go ahead and make your selection now, and then when I get to the answer, hopefully we agree. So, an engine making knocking noise with the transmission in drive. The noise is not heard in park or neutral. We have 4 choices of what could be the cause. Excessive main bearing clearance, low oil pressure, a cracked flex plate, or a broken piston ring. So let's start digging into these a little bit here. So on answer A, ask yourself, would excessive main bearing clearance be different in neutral or drive? Make sure you use all of the information provided in the question. It's not just a knocking noise, but it's a knocking noise in drive. Then the additional information that it's not heard in park or neutral. So if we have excessive main bearing clearance, would it make a difference whether it's in neutral or drive? Same with low oil pressure. Dropping it into drive, is that going to change the oil pressure? Okay, think about your answers on this. Answer C there, a cracked flex plate. The only way you would be able to answer this is if you know what a flex plate is and the difference versus a flywheel, okay? And then D, a broken piston ring. Does the piston ring, the condition of the piston ring, is it going to change when we go into neutral or drive, going from park to drive or neutral to drive, is it going to change? Okay. So here's the quick answers on that. No, the main bearing clearance is not going to change. The oil pressure, if it's already low, putting it into drive Yes, I understand there's an argument to be made that the engine RPM is going to be a little bit lower, so therefore oil pressure potentially a little bit lower, but not enough to make a knocking noise come and go. And then answer D, no, would be the answer. The piston ring, the condition of it, say if it's broken, it's not going to suddenly unbrake or quit making noise just because you've put it into drive. So the correct answer for this one is a cracked flex plate. The flex plate is put under load when in drive. So let's talk about flex plate real quick. Flex plate is on the end of the crankshaft, the rear end of the crankshaft between the engine and the transmission. We use a flex plate when we have an automatic transmission. It's much thinner, but it still has the ring gear that's used for engaging the starter motor. But it's much thinner and lighter, and it just provides a way to attach here in the center to the crankshaft, the output of the engine, and then you can see these bolts around the outside where the bolts connect to the torque converter. It's different than a flywheel. It's in the same location between the engine and the transmission, but we have a flywheel when we have a manual transmission. The flywheel is much thicker, usually made out of cast steel or cast iron. Also has the clutch cover and disc attached to it, so there's a lot of mass there with a flywheel. We don't need that much mass when we have an automatic transmission because the torque converter part of the transmission that attaches to the flex plate is quite large and quite heavy, and so it provides that mass. This one here is a classic example of a cracked flex plate, and you can see this one is literally what looks like just 1 or 2 inches away from being completely cracked through. If somebody drove this vehicle into the shop, they got there on a hope and a prayer. All right, question 2. An engine is overheating and has white smoke coming from the tailpipe. The cooling system is pressure tested and will not hold pressure. So let's start real quick here by looking at our question, and then we'll go into the answers. We have multiple symptoms here, or multiple bits of information. And again, I want to encourage you to make sure you use all of the information provided, not just a part of it when making your selection. I also want to point out that the first question and this one, they're both your classic ABCD multiple choice answers. So there's only one possible answer, and it's very straightforward. Not as tricky as those Tech A, Tech B type questions that we'll look at in a little bit. But notice what we have here. Engine is overheating, so we have a symptom. White smoke, we have another symptom. Cooling system, pressure testing will not hold pressure. We have 3 symptoms that we know this engine is experiencing. Okay? Most likely the smoke or the overheating was what brought it into the shop. Someone did a quick pressure test on it. Cooling system's not holding, so we have 3 bits of very relevant information. So let's look at our 4 answers now. Option A, a blown head gasket. B, a restricted piston nozzle. C, a stuck open thermostat. D, an incorrect PCV valve. All right, are you thinking about your answer? Okay. So, as mentioned, I'm sorry I didn't highlight the overheating, but we got high overheating, white smoke, and cooling system will not hold pressure. So I jumped straight here to the answer on this one, but I'm still going to talk about it a little bit with you to help work through the process if you didn't already have your answer as option A before I click to this slide. So a blown head gasket, yes, it can cause white smoke and coolant leakage. Now, what are we talking about with white smoke? We generally, in automotive diagnostics, we deal with 3 different colors of smoke. White is most often associated with the burning of coolant, antifreeze, or even water. If it's very diluted and it's mostly water, it'll still be white smoke, but it might look like steam and it might dissipate much more quickly, where coolant antifreeze will leave a much more lingering cloud in the shop that hopefully you get blown out the door pretty quickly. Okay. One of the other types of smoke that we can talk about is black smoke. Black smoke is typically from unburned fuel. So we have too much fuel entering the cylinder, being compressed, being ignited, but part of the fuel is only partially burning, so it's being left in a carbonized state, if you will, that black color, and then being exited through the exhaust system. So black smoke we generally associate with too much fuel or a rich condition. And then we have what most call blue smoke. And blue smoke is when we're burning oil. Not talking about oil that's gotten onto the exhaust, but if you've ever seen that, the smoke off of that from like a leaking valve cover is kind of bluish. But we're talking about a large quantity of blue smoke out the tailpipe. That's usually associated with oil that's been through combustion. Okay, so not from other sources, but actually been into combustion, meaning into the air-fuel mixture, compressed, ignited, the oil burns, and it typically leaves a blue smoke. All right, enough talk about smoke. Let's get back to our white smoke here. Blown head gasket can cause white smoke because of coolant entering that combustion process. And remember, we also have coolant leakage as one of our symptoms. So that's certainly the combination of the white smoke, the coolant leakage could certainly lead to an overheating condition. Restricted piston oil nozzle, you might not be familiar with that, but this is the A1 test series, so it is a part of the engine. Some manufacturers call it the piston cooling nozzle. Basically, it's inside the crankcase. It's a nozzle that points upwards towards the bottom side of the piston, so not the top, not in the combustion chamber, but in the crankcase on the bottom side of the piston by near where the wrist pin is connected. Spray oil up underneath there to help cool the piston head or crown, whichever term you prefer. Also provide some additional lubrication to the wrist pin connecting rod. But again, will not cause white smoke. If somehow it was in getting oil into combustion, again, it would be that blue smoke. A stuck open thermostat would not cause cooling system leakage. Same with answer B, I didn't mention that. With the piston oil nozzle, also would not cause cooling system leakage. Again, remember all of the information you're provided with the question. Incorrect PCV valve, again, also would not cause coolant system leakage. Let's look at a head gasket here. You might be going into this test and maybe you haven't done a lot of internal engine work yet, but between the cylinder head and the engine block, we have typically what's referred to as the head gasket, where the two large surfaces are clamped together. And this large hole in the middle, of course, is for the piston, for it to be able to come up into that area. And then along here, we have these passages that allow coolant to flow vertically alongside the cylinder and maybe even all the way into the cylinder head. And the black portion here, that's a part of the sealing material. And typically they have some metal layers in the center of the gasket, in the middle layers. You can see here where the black portion is all blown out, allowing compression and engine coolant antifreeze to swap places. So we could potentially end up with compression in the engine cooling system, blown hoses. In the case of this question, we are getting coolant that's going from the cooling system into the cylinder and then being burned. All right, question 3, again, another multiple choice one. So far we just have standard multiple choice questions in these examples out of the study guide. This one says, an engine compression test identifies that one cylinder has low compression. So one cylinder, low compression test. During a leak down test of the cylinder, excessive leakage is observed and air is heard coming out of the tailpipe. Which of these could be the cause? Okay, I'm not going to get terribly into the details of performing a leak down test, but I can tell you, just for sake of brevity, if you're not familiar, it's basically a test where you're blowing compressed air into the cylinder. So you have the piston all the way at top dead center. You have the valves, both the intake and exhaust valves, in the closed position. You adjust and calibrate the test equipment, and then so where it's set at 0, and then you connect it to that cylinder where air starts blowing into that cylinder. If it were perfectly sealed, you would have 0% loss. You always do have a small amount of loss. So in this question, they're saying that that test is being performed on a cylinder that we already know has low compression. We're trying to figure out whether or not it would be beneficial to the customer client to remove the cylinder head, or some repair where we could provide an estimate. Or maybe we need to provide an estimate to do a teardown for future exploration. Or maybe, based on the mileage and what we find from the leak down test, maybe it's in their best interest we jump all the way to a short block or a long block. Okay? So we do these sorts of tests not just to entertain ourselves, but so that we can make informed, professional recommendations to our clients, right? So air is heard coming out of the tailpipe. Which of these could be the cause? Broken piston rings, a blown head gasket, a leaking exhaust manifold gasket, or an exhaust valve not sealing. I already told you very briefly what the test is doing, blowing air into the cylinder. The piston should be at top dead center and all of the valves closed. All right, do you have your answer? Okay. Oh, I forgot I had highlighted a slide here, just highlighting again, using all of the information you're provided. One cylinder, excessive leakage, and coming out of the tailpipe. Okay. I already talked about what a leak down test, what is a leak down test, and where would the air escape with each of these choices. So A, B, C, and D. If they were a fault, where would you hear air coming out? Okay? Drum roll, please. Answer A. If it was broken rings, air would leak out of the crankcase. So maybe taking off the oil fill cap or pulling the PCV valve or something where you could hear air coming past the rings, through the crankcase, and then out the ventilation system for the engine. If it was a head gasket, okay, and it was leaking between the cylinder and the engine cooling system, like we saw in the last test question, well, we could take the bottle off, the cap off the expansion bottle or off the radiator, and good chance we'd see air bubbles coming out of there. Option C here, a leaking exhaust manifold gasket. Okay, we're talking about the gasket between where the exhaust manifold bolts to the side of the cylinder head. So it's not under pressure at all when we're doing this test. If it is, there's something really crazy going on. And then D, an exhaust valve not sealing. Well, that is your correct answer, because air is bypassing the valve. So maybe we got a bad seat, a burned valve, bent stem, something to that effect. We have an exhaust valve that is not sealing. So the air that's being pressurized into the cylinder with the test equipment is going out through the exhaust, and that's why you can hear the air coming out of the tailpipe. Okay, so here's an example of a very well burnt exhaust valve. Generally, the intake valves, especially in just a 2-valve system, cylinder head like this, the intake valve is going to be larger, because remember, it's bringing in air and fuel. Then the exhaust valve is typically, but not always, a little bit smaller, because it's just exhausting, again, those inert, meaning spent gases and whatever's remaining in the cylinder. So this one's kind of had what we used to call the blowtorch effect done to it, where it probably had some carbon, and then over time, from the flames whizzing by, it completely torched or ruined that valve, and that you can see where air would be just going right past that, and you'd hear it coming out the tailpipe. All right, on this one, we're getting into some cylinder head measuring type stuff, and I've kind of expanded the slides going through this series here to try and help illustrate what they're actually asking you, because you can see there's not a ton of information in the question, but then we have this picture that they've thrown in. So just reading the question, a technician is reassembling a cylinder head. In the illustration shown, which of these is the technician measuring? Now here I've reformatted this question to put the question and the answers all off on the left. Hopefully you're getting a big enough view. Here, let me even give you a minute or so with the extra large view. So the question is asking, what are you measuring? So you can see that they're illustrating a ruler there, and we see that he has it against what looks like the surface of the head, right, where the valves are at. And we see the valve spring, the retainer, and the keepers, and we see then the stem. But he doesn't have a straight edge or anything coming across over to the stem. So just keep that in mind as you're looking at this. Okay, so what is this technician measuring? Is he measuring the installed stem height? Okay, the valve stem installed height. Is he measuring valve spring squareness? Whether the coils of this spring, whether or not they've gotten wonky, or whether or not they're still in a nice circular row from top to bottom. Okay, is he measuring the installed spring height? Or is this technician measuring, and I don't mean to keep saying he or she, are they measuring the valve spring pressure, right? The amount of pressure that this spring is applying between the retainer and the cylinder head. Okay. I want to ask you how, with what we're looking at here, can we maybe eliminate a couple of the answers before we even go on much further? Remember, I told you a part of these intros I do for the ASE training I provide is to just get you used to reading the questions and then some test taking techniques. Again, we have a classic 4-part multiple choice question here. Can we maybe eliminate installed stem height, since unless this guy's just completely winging it and eyeballing it, that there's no way that this technician is accurately measuring the stem, which would be clear over here. We would need some sort of additional like slide coming off of this ruler to pretend that's what he's doing. And the valve spring pressure, can we pretty much agree that this technician is not measuring the spring pressure, that the spring with what's being inspected here, the technician is going to have no way of knowing how much pressure that spring is exerting, where if you were to remove these valve keepers, is the spring going to come flying off at 100 miles an hour, or does it barely have any sort of pressure put on it at all? So hopefully you agree with me, we can eliminate those two. Okay, so let's talk about valve spring squareness. And again, this is not a whole course for A1. This is just going through the study guide practice questions for 23-24. Valve spring squareness is measured uninstalled when you have the spring in a fully relaxed state. It's just natural state, it's off the engine. And that's when you measure the springs for squareness. That's when they're completely uncoiled. And if there's going to be weirdness, that's when you're going to see it. This is not a textbook answer, but what we used to do, the first quick test, if we had a good workbench, was just to roll them across the workbench. And if they rolled straight, then good chance they were going to pass the test. If you rolled them across the bench and they start going in circles, good chance they weren't very square, that they had become tapered. Keep in mind that measuring the squareness of a valve spring only applies on engines that are supposed to have nice, square, parallel springs. There are tapered valve springs on some engines. So don't think that all engines in all countries for all manufacturers have square coil springs. Okay? So our answer through process of elimination is this technician is measuring the installed spring height. And there's a number of ways that can be done. The one being illustrated here by ASE, in my opinion, is one of the least accurate. But really the amount of accuracy needed would really depend upon the type of engine and then what type of valve train is going to be operating these valves. Are they going to be kind of a traditional rocker arm with a push rod? And if so, are the rocker arms adjustable? If yes, then the valve stem, the installed spring height would be important, because you would want to make sure it wasn't too short, because when the valve gets pressed open, you wouldn't want the coils to be binding, Likewise, you wouldn't want it to be too tall and risk there not being enough spring pressure, keeping the valve and the seat in a nice closed position. But if it's an engine where maybe over the top of this is now going to set a cam carrier and it's going to have cam followers and who knows what, then the installed spring height is going to be very important and would probably, in my opinion, warrant a more accurate test than just holding a ruler up like is illustrated here. Here's an example of a more accurate tool. You can see this technician has installed just the inner spring. A lot of valve spring systems now have an inner and an outer spring. I won't go into great detail on that now, but that's covered in later training materials if you should so choose. So they have the inner spring installed just so that it's keeping the valve in an all the way up position. And then they actually have a micrometer in here that out on the end that you can't see would be to the left off of the side of the illustration is a thimble where they can turn it, get that exact height down to probably going down to the thousandths or 10,000ths or something to that effect. Probably not 10,000ths, I probably should just say thousandths. Getting that exact height, and then they know they have an accurate measurement. All right, here we go. This is our first Tech A and Tech B. If you've watched any of my other intro and training videos, this is where I tell you that anytime you see Tech A, Tech B, it's 2 questions. So answer Tech A's statement, set that aside, answer Tech B's question, then take the 2 and combine them together, and that's the only way you can answer a Tech A and Tech B question accurately. Another thing I like to mention is sometimes this whole Technician A, Technician B, if that kind of, bothers your brain, I completely understand. That's why you've heard me say in other training videos, I call them Adam and Bob, but I'm a middle-aged white guy. Maybe you want to call them, Adrian and, some other name, Beatrice or something. Come up with a way to where when you get to an A-B question, you're not, if it's affecting you, the stress of the A-B questions, just come up with something that can maybe humor you along the way. Like, oh, I remember that redheaded guy at autoshopteacher.com on YouTube talking about Adam and Bob. If you want to use it, by all means, roll with it. Adam and Bob. Maybe the whole Technician A, Technician B thing doesn't even register for you. Great. Then forget everything I just said and let's get into this question. Number 5, an engine produces blue smoke. Uh-oh, we've changed the color of the smoke. I already gave you the speech on the smoke. An engine produces blue smoke when accelerating from a stop. Here we go. Our first question. We have our fact. An engine produces blue smoke when accelerating from a stop. Technician A, Adam says that worn exhaust valve guides could be the cause. So think about the information we have. Engine produces blue smoke when accelerating from a stop. So it's very specific. Blue smoke and accelerating after we've been sitting at a stop sign or light. Tech A says that worn exhaust valve guides could be the cause. Okay, you got your answer on that? Basically, you're trying to agree or disagree. With these Tech A, Tech B, either one's right and the other's wrong, or vice versa, or they're both making up lies and they're both wrong, or they're both right and they might be telling you 2 different things, but both of the things that they're telling you is right, and in that case, answer C would be. So, do you agree with Technician A? Now let's look at what Tech B, or Bob as I call him. Bob says that worn exhaust valve seats could be the cause. Who is right? Okay. So let's look at this here. They are saying the exact same thing up to this point in this question. See that? Make it bigger for a minute here. They're saying the exact same thing up to A is talking about the guides and B is talking about the seats. Hopefully you know about valve train and valve systems. I'm not going to go all into that right now. Again, this is just the intro video. Okay, so they're talking about guides and seats on the exhaust valves being worn. Here's your reminder. What kind of smoke are we talking about? Blue smoke, so typically an indication of burnt oil, oil that's been through combustion. Tech A, again, is talking about the guide. B is talking about the seat. And my question to you, as you're choosing your answer for this one, will either of these cause oil in the cylinder? The exhaust valve guide and the exhaust valve seat. And remember, my question comes with the same conditions as the question here. We're talking about blue smoke, and when I say will either cause oil in a cylinder, well, I'm including the when accelerating from a stop. So we're not talking about sitting overnight. We're not talking about parked at the grocery store or grandma's house at Christmas, okay? We're talking about the engine's running, there's no blue smoke, you accelerate from a stop sign. Will an exhaust valve guide or exhaust valve seat suddenly allow oil to enter into the cylinder when you accelerate? Neither, okay? So in this case, both Adam and Bob, or Tech A and B if you prefer, they're both wrong answer. Neither one of them is right, and you will have these where both techs are wrong. They're both feeding you a line. So don't be afraid if you know you've answered Tech A's question. No, he's not right. Tech B, no, he's not right. Don't be afraid to pick D. Moving on now. Question number 6. To determine piston to cylinder wall clearance, the diameter of the piston shown should be measured at, and we have 4 choices. These get a little weird because they give us 4 choices, but of course the piston is not marked. The 4 spots there we can see are marked W, X, Y, and Z. Okay, they don't mark them A, B, C, and D. So there's an additional part of this question besides knowing where you need to measure the diameter of the piston correctly, okay? Because you got to measure the diameter of the piston, then you got to measure the size of the cylinder and subtract the one from the other, and that's how you find out the piston wall clearance, right? Hopefully you knew that already, but that's the process. So you got to measure the piston, you got to measure the cylinder, find out what the difference is, and that's how you can determine the clearance. But once you know this, and let's say you wanted to pick X, you got to then come over here and pick where X is. Do not always expect X to always be in the second spot. Our A, B, C, D over here could just as easily be in a mixed up order and be X, W, Z, Y, or something to that effect. So pick your answer over here. Okay, it's X, and then make sure you come over and find out where X is on your choices of answer. All right, now let's get into talking about our answer for this question 6. So the diameter of the piston should be measured at what point? We have way up here at the top. We have here just below the oil ring. We have here in the middle. And we have clear down here at the skirt. Hope you have your answer. Let's move on. Here are 2 additional diagrams I brought in. The one on your far right over here. Let me make this larger. This one over here on the right, that's straight out of the practice exam study guide, the ASE study guide. These other 2 are out of textbooks I've used in my automotive fundamental classes in the past. You can see with the ASE one, we're looking at it with the wrist pin hole here facing us. The middle one's orientated the same way. The one on the left, I realize it is turned sideways. But I wanted to give you both of these so we could talk about the different parts of a piston, but just just in this kind of basic sense. Again, this isn't the full-on training for A1. This is just us going through the practice questions to see if you're ready. Okay, so you can see the skirt diameter. I'm using the middle illustration here. Look at this line. Is actually the largest part of the piston. Okay, the head, or if you're old school, we were taught the crown, but the piston head or crown, the top of the piston, to just describe it, the head is actually smaller. Okay, so keep that in mind. Over here, the reason I brought in this additional illustration is because, so you can see I'm not making up terms. This textbook actually calls it the piston head. And then where the rings are at, those grooves around the piston that the rings set in, those are called the lands, okay? And then the bottom one would be the oil ring groove. And it's different than the other grooves where it has these holes that are inside in the bottom of that groove, and that's where, after it's wiped the oil, that's how it gets back into the crankcase and down the inside of the piston and drips back down into the crankcase, okay? Then we have the piston hole, okay? Just for, we're using very basic terms here with this illustration. The pin bosses just means that's the reinforced material here where the wrist pin goes through. And then the skirt, okay? Going back to our middle illustration. Sorry, I need to get a drink of water. Back on our middle illustration, the skirt is your largest part of the piston, okay? Let me back up one slide here. And you can see we do have 3 of our choices are down here on the skirt, okay? And let me go to the next one. So, to determine the piston to cylinder wall clearance, the diameter of the piston shown should be measured at Y, okay? The middle of the skirt. And I know I kind of jumped to that quick. Let me back up here. Here on the skirt at the very end, the bottom, so I'm on the far left image. Hopefully you can see my little mouse pointer here. We wouldn't want to have that to be flared out, or as that piston's coming down through the cylinder, it could be scraping the cylinder wall. So it's typically going to be a little bit narrower. And then here right below the oil groove, as illustrated by X on our right image, that's right below a ringland, okay? And you could measure this piston anywhere you wanted to, okay? But if you wanted to jump straight in for where most likely the widest spot is going to be, it's going to be here at Y. And that's because it's, if you will, the most protected. You have the rings up here. Remember, even though the top upper portion of the piston is smaller in diameter, it still has those rings, the compression rings, oil ring, that are filling in that gap between there, okay? So it's still sealed, but the most protected part is going to be Y, because it's probably going to be the most lubricated, and it's definitely going to be the thickest or heaviest or hardiest part of the piston. Here is showing using a caliper, a micrometer, excuse me, to measure here in that area, that portion of the piston. Hopefully that gives you a little bit of an idea of why you would measure there. But I want to point out something from this stock image photo. This technician is not using this micrometer correctly. This large part of the thimble, yes, you can turn it there where this technician is when you're making massive adjustments. Let's say you're moving this thing 1/4 of an inch, get it down to whatever you're going to measure. But then as soon as you start getting close, the fingers should be out here on this end portion of this micrometer. That is called the thimble, or as my auto shop teacher clear back in 80s high school auto shop used to call it, the great equalizer. Because whether you're, whatever you want to say, Hulk Hogan, Arnold Schwarzenegger, whatever, some muscular bodybuilder, Vin Diesel maybe, you can crank on this as hard as you want, and it's like a ratchet. It's just going to click, 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 click. You can only tighten so far if you use the thimble. Or if you're an 80-pound, gymnast or whatever, I don't know who to say wouldn't be strong, but whatever. If you don't have a lot of hand strength, still, you bring down this micrometer until it's making contact with the surface you're measuring, and you turn this thimble to the point where it starts clicking, you're done. That's your measurement, then read the micrometer. All right, moving on. Question number 7. Technician A says that the setup shown can be used to check the cylinder taper. Technician B says that the setup shown can be used to check the cylinder out of round. Who is right? Remember, Tech A, Tech B. So it's 2 questions. Look at the illustration here. Let me jump ahead and see. Yeah. Okay. So we got A only, B only, both A and B, neither A and B. Hopefully by now you're used to the whole Tech A-B thing. So we really just need to figure out what is this illustrating, and can it be used to check cylinder taper, as Technician A is stating, and can it be used to check cylinder out of round, like Tech B is saying. So here is a more modern version, if you will, of this tool that's being illustrated in this black and white drawing. You can see this one here that I pulled up is has a digital display, like a lot of our measuring tools do now. I still think you should learn how to read a traditional mechanical analog micrometer, but these tend to be very accurate if they're kept calibrated. A lot of them even come with a way to recalibrate them yourself now. So here is a modern version of what's being illustrated in the ASE practice question. We can see it's down here in the cylinder, right? They've cut a nice hole in the side of the block for us. We're looking right into the cylinder. And again, we're questioning, can it be used to measure the cylinder being out around, as well as if the cylinder is tapered between the top and the middle and the bottom. So the way this works is you pick the right dowel to add to it here, like 2 inches or 4 inches, and then you already have the width of the tool itself, and then you're taking this and you're placing it down inside the cylinder, and then you're making a measurement. So hopefully with that brief description of what the tool does basically and where it's placed, hopefully you got your answer, right? Tech A, cylinder taper. Tech B, cylinder out around. Who is right? So you answer Tech A, you answer Tech B, and you come up with your answer. Well, Tech A is right, yes, but, Tech B is right, so yes, but, remember, if they're both right, you got to make sure you mark C, because you could answer A, but remember, the answer for A and for B is saying that technician only. When they're both right, or as we saw in the last question, both wrong, you got to make sure you get that C or that D. You can't just read half of it and answer half of it. You have to answer both questions that are in any of these A and B type questions. Question number 8. An engine overheats at higher RPMs and returns to normal temperature at lower RPMs. Which of these could be the cause? So I'm going to read through that again. Overheating, higher RPMs. Normal at lower RPMs. Okay? Which of these could be the cause? We've gone back to a traditional 4-answer multi-choice question. A stuck-on cooling fan relay. A worn water pump belt tensioner. A restricted heater core. An incorrect coolant concentration, meaning somebody didn't mix it exactly 50-50. Okay? So remember, what was it, 2 or 3 questions ago? When you're unsure, start eliminating possible answers. That's the same thing I'm going to suggest here. Start eliminating one. Can you eliminate A? Can you eliminate C? Okay, which ones can you eliminate? And then start taking the information. Wait a minute, okay, it's saying overheats at high RPM, so that's high engine speed. Okay, And it's not saying necessarily fast vehicle speed. Also keep that in mind. Okay, high RPM doesn't mean you're going 80 miles an hour. It means RPM, engine speed. So you might be going 15 miles an hour, but it's in first gear. Keep that in mind, okay? So, continuing on. Can the cooling fan relay cause this? Well, if it says it was faulty, possibly, but this says stuck on, meaning the fan's running all the time. Well, I think not. What about a worn water pump belt tensioner? Well, when the engine's at slower speeds, it's okay, but then at high engine RPM, if that belt tensioner is bad, could possibly the belt be slipping for the water pump? Think on that. Restricted heater core. None of the information given to us in the question is talking anything about HVAC. By that I mean heating, ventilation, and air conditioning. So is the heater core even really a play in this? And does the heater core, which is used to provide heat to the passengers inside the vehicle, is it going to change or affect this high RPM versus low RPM? And then an incorrect coolant concentration. Now, we don't need to sit and debate if it's whatever, that it's got, 100% coolant that they got from some third world country. No. The question or this answer just says incorrect coolant concentration. So they didn't mix it 50-50, it's 60-40 or whatever you want to say. So don't add into the answers when you're reading these. Okay? So hopefully you can eliminate A and C right away. Okay? Because if the fan was stuck on, definitely is not going to contribute to an overheating problem. And heater core, it's not even a player in this question that we're trying to answer. So, can incorrect coolant concentration cause this? Okay, I realize somebody's probably going to private message me on this or whatever. But again, do not read or add information into the answers. Just take it. It doesn't say coolant that's so thick it won't flow through a garden hose. It doesn't say that. Answer D says an incorrect coolant concentration. Just leave it as simple as it's stated, okay? So, back to B, can a worn water pump belt tensioner cause this? Yes, it certainly can. It can allow the belt to slip because there's more restriction put on it at a higher RPM. It's trying to move a higher volume of coolant. So the impeller inside the water pump has more resistance. The belt's more likely to slip. Number 9, a fuel-injected engine has low fuel pressure at the fuel rail test port. This could be caused by a restricted fuel filter, a restricted fuel injector, a stuck closed fuel pressure regulator, or a shorted fuel injector. Gotta make sure I read and enunciate properly. All right, so we know that we have a fuel injected engine that we're doing a fuel pressure test. It has a low reading, and we know where we're connected. We're connected to the test port located on the fuel rail. Okay, so it's some sort of fuel injection type system that uses a rail type. So either a common rail GDI or maybe it's port fuel, doesn't really matter. And since we're not told, we don't need to add that into our factoring for the answer on this. So we're talking about low fuel pressure at the test port. And just ask yourself, as you go through each of these, could a restricted fuel filter cause that? Could a restricted fuel injector cause that? Okay, we're talking about the supply, the fuel pressure. If the injector is restricted, would we maybe be talking about cylinder misfire or a cylinder that's lean? Okay, a stuck closed fuel pressure regulator. Well, only if you're familiar with how a traditional mechanical, I'll say, type fuel regulator works, would you know stuck closed what that would mean? So we're going to look into that. And then a shorted fuel injector. Shorted, we're now using electrical terms, okay? Shorted fuel injector. I can tell you, I'll just go ahead and let that one out. That's going to cause possibly the injector on an electromechanical hydraulic type injector to not open, okay? Or if one circuit's shorted to ground, then maybe to never close if the power's applied. But just make sure you're looking at the terms that they're using. Restricted, restricted, stuck closed, shorted. Wait a minute, shorted? We just switched to an electrical answer on D. Okay, low fuel pressure at the fuel rail test port. So restricted fuel injector, I'm going to go ahead and eliminate B. Hopefully you have already as well. That's going to cause fuel to possibly not make it into combustion, into the cylinder, to the combustion process, but it's not going to cause the fuel pressure, the supply to the whole fuel injection system to be low. Okay? Shorted fuel injector, I already let that one out of the bag. No, it's not going to cause the fuel pump and fuel supply system to have an issue because a fuel injector is shorted. You might have a blown fuse or some other symptom or condition, but it's not going to directly affect and cause just low fuel pressure. Remember, it doesn't say no fuel pressure, it says low fuel pressure. Okay, so stuck closed fuel pressure regulator. If you're still debating this question, this is probably, answer C is probably the one that's got you hung up on this one. So let's talk about it. Here's just a basic illustration of a fuel system, what we call a return type fuel system. So we have a fuel pump module or pump in the tank, which has wiring going to it. We know that the fuel pump is at least getting power in the question that we're trying to answer because we have fuel pressure. It's just low. Fuel pressure comes down a line, typically through a filter, then enters the fuel rail, comes around through the fuel rail. In process there, it provides fuel to all the injectors. And the way that we make sure that all the fuel injectors get the same amount of pressure is by putting a restriction here before we return what's left over back to the tank. So by putting a restriction here that we call a fuel pressure regulator, think of it kind of like the dam that's going to hold the water, or in this case the fuel pressure, up to a certain point. Once that amount of pressure is reached, the excess pressure that's unneeded returns back and drops into the tank. That's why we call this a recirculating type fuel supply system, because the excess fuel is returning. So either a recirculating or a return type fuel supply system. So our question, one possible answer is that this, I'm going to back up here, stuck closed fuel pressure regulator. So what does stuck closed do? Okay. This, as the pressure overcomes, once the pressure is reached, sorry, I jumped around the slides there. When the fuel pressure, again, use that dam analogy, once it reach, that's funny, dam analogy, right? When the water reaches the top of the dam and it flows over, well, same thing here with the pressure regulator. When the pressure reaches whatever it's been calibrated to, then it opens to let the excess fuel pressure go back to the tank. So if it were stuck closed, then the pressure would be too high. Okay? So our only option on this case would be A, if the fuel filter was restricted, then the fuel pump is down here and it's just going like crazy trying to get fuel to the fuel injectors, but it's trying to push it through a fuel filter. I know that was kind of a winded answer on this one, but if these questions, remember this is the A1 practice test and we're dealing with a fuel system here. Remember, there is a small percentage of these type questions on the A1 because even if you're a heavy line engine tech, there's a high likelihood that you might have reassembled an engine or something and it's not lighting off, right? It's not running after you've gotten it back together, and you might be expected to do some basic preliminary tests. And that's why they have these questions in here. All right, our next one is, I believe, our last one, question 10. ASE loves to throw these in at the end of the practice series, and these can be very tricky. I'm going to try and not go too long on this one, but just keep in mind, when you see the word accept in an ASE question, doesn't matter which exam you're taking, you're going to have 3 right answers for what they're saying. You're looking for the accept, which means you're looking for the wrong answer, if you want to think of it that way, the exception. So, question 10, an engine with a variable valve timing system has a stored VVT performance diagnostic trouble code. Any of these could be the cause, except. So this is where it gets backwards. Any of these could be the cause, except. When you see that, that means you're getting ready to read 4 statements that 3 of them are the right answer. Any of these could be the cause, but then you're looking for the except. Our 4 choices are a stuck open oil filter bypass valve. Make sure you always read the whole description. Okay? Which bypass valve? The oil filter bypass valve. Restricted oil control screen. Sticking camshaft actuator or phaser. Those are synonyms. Some manufacturers call them actuators, some call them cam phasers. Restricted oil pump pickup screen. Think about this one. So hopefully a couple of these you're already thinking, yeah, that could be causing VVT fault code. All right, let's look at this. Again, just to drive home the point, we're looking for the except, meaning we're looking for the wrong answer, or to more properly say, the answer that would not cause what's being described. Okay? So start by finding the could, if it's easier for you, rather than trying to eliminate in reverse. Go through and say, okay, I'm going to replace the word accept with could, and I'm going to find the 3 that could, and the one that's left over is my accept. Okay? So could a stuck open bypass, oil filter bypass, could a restricted oil control screen, could a sticking camshaft actuator phaser, or could a restricted oil pump pickup screen. And on this one, I'm not going to go completely into detail. Again, this is not the ASE A1 training. This is a review and an intro review of the practice questions from the study guide. Hopefully, as you go through this, if you've been having trouble with agreeing with my answers, they're not my answers, they're ASE's answers, they're ASE's questions. But if some of these are like a second language where it's not making sense, a foreign language I mean to say, then that's what I'm here for, to help with training, okay? And I offer even one-on-one sessions where we connect online. We can work on assignments together and discuss things. I can even provide you specialized training in just certain portions of the test. Get in touch with me, okay? But I'm not going to go into describing what a whole variable valve timing system is for this intro video, okay? So A is going to cause no oil filtration. Because remember, and I already pointed it out, we're talking about the oil filter bypass. Oil filter bypass opens when there's too much restriction in the oil filter, and so it allows oil to still circulate throughout the engine by bypassing the filter. It's a very bad condition, but it's going to cause no oil filtration. Restricted oil control screen, well, that's going to cause no oil through that VVT solenoid. Camshaft actuator or phaser, it's typically going to be a more consistent issue, okay? Remember, and I point out consistent because we said that this has a stored, not a current fault code. So it's stored. Now, again, we can't read into this information and know whether this was a key-on engine running test. We don't know, but we do know that it says it's stored, okay? Not trying to get into word semantics or into the A8 and L1 type of test questions, but just keep an eye out for little bits of information like that. And a restricted oil pump pickup screen. Well, we would have low engine oil pressure, right? So the stuck open oil filter bypass valve could not cause, so then there is your accept. So here again, we just had a question, the one before last, I think it was question 9, just to point out here, you are going to have 7 questions relating to fuel systems, electrical, ignition, and exhaust systems. So that's why we had that question 9. Okay. Obviously, we had them on cooling system. And as we just went through those 10 questions, we kind of hit all the bases here. But don't think just because it's the A1 test that you're not going to have any ignition or fuel or, that's for those engine performance techs. I'm a heavy line tech or I'm an engine builder or whatever. You do need to have some basic knowledge and skills even in fuel, electrical, ignition, and exhaust systems. So again, I'm Brian D. Wampler. I have autoshopteacher.com and Brian D. Wampler on YouTube. Love to hear from you. Reach out. Let me know if I can help. And I'm here. Thank you.